Record. Alrighty. To start off, this is a video I thought was kind of fun from some folks at CMU and NVIDIA recently. It'll play, but it's basically a robot humanoid doing this too. And so it's a pretty cool method. They basically what they do is they train models in simulation and then they like transfer them to the real world. But they do a little bit of data collection in the real world to adjust for the gap between simulation and real. So check it out. It's the algorithm called ASAP, but I thought it was pretty cool. Alrighty, so where are we? We've covered feedback control. We talked about PID control. We studied some LQR. We're going to do a little bit of MPC today, and then we'll study Lyapunov theory a bit, right? So let's start with a little recap. So start some logistics. Series paper discussion is going to be next Wednesday. Two papers. One is on autonomous driving, and one is on MPPI, which is a planning or a control method. But homework 3 is due on Thursday, I think. So, yeah, get started on it soon if you haven't already. Okay, here's our little quiz. LQR solved by dynamic programming, random search, PyTorch, graduate student. There's 15 answers, but not 15 people. Zoom loophole. Alrighty. 5 more seconds. Okay. Good. All right. So let's do a little recap. So we talked about LQR. So LQR is a system which is linear dynamics for quadratic cost. And we solve these equations called the Riccati equations to kind of get this recursion, which looks something like this. You can solve for a Ki and a Pi, where your control, U is equal to Kix, and your cost is quadratic with the coefficient Pi. Right? And so we know that because it's linear and it's quadratic, when you solve the problem backwards, it gives you a closed form solution. And so you just need to solve it with matrix multiply. No need to do anything approximate. It's exact when it is when it's truly linear and quadratic. Right. And so the nice part is that it gives you these exact equations. Optimal controller is linear, optimal cost is quadratic. And as a result, it's super duper efficient. Like you can run this in real time. It's really fast, especially for most reasonable size systems. So the LQR algorithm kind of works like this. It's saying that you recursively start from the back. You compute Pi and Ki. So Ki depends on Pi minus 1. Pi minus 1 starts at Q, right? And then you go backwards, you compute Ki. Ki will be used to compute Pi, and you keep going, right? And so you go backwards from the last time step to the first time step, compute Ki and Pi, and then you play control equal to Kix forward. Right? No matter where you are, you play Kix. That's an optimal controller for LQR system. Okay. Now, intuitively, we unpack this to say that the cost is a combination of 3 terms. The first is the current state cost. So like how much are you penalizing the current state? The second is an action cost. So how much does the magnitude of your action hurt? And the third is kind of like measuring what the optimal cost in the future is going to be, right? So you can see that the terms that have to do with dynamics A and B kind of show up in the future term. And so it's a combination of the current cost, the current action, and the future cost. So inherently, you always trade off the current versus the future. Just like we talked about this a little bit, but it's the dual of Kalman filtering. In Kalman filtering, you trade off your uncertainty versus your current sensor. Here, you trade off your current cost versus your future cost. Okay, so now you want to go beyond linear systems to nonlinear systems. Let's say you have some nonlinear system. F of x ut. What you do is you try to approximate it with a Taylor approximation. So you see that you're going to approximate an f of x t ut around some point x star u star. So you're going to do a Taylor approximation. It's a multivariate Taylor approximation. So you're going to approximate around x star u star. And this is like the first order Taylor approximation with respect to x and with respect to u. Okay. And so you can show that it's a linear system. so you see this thing is linear in X and this thing is linear in U. Right? And so while this doesn't look linear at first, you can kind of rewrite it to be linear in X and linear in U. You do a little bit of change of variable. You write xt minus x as z and ut minus u as v. And then you can show that this is exactly a linear system. And so this kind of leads to a class of algorithms called iterative LQR, which we won't go into in much detail, but basically the idea of iterative LQR is you like execute your controller. You get a set of states, you linearize around those states, you get the optimal controller, then you execute again, get new states, you linearize around those states, get your controller and repeat. Right? And so it's iterative LQR. So you like repeatedly keep linearizing. And the point is that because your system is nonlinear and the linear approximation is only valid in a small region, you have to keep relinearizing. Okay, so this is like the core idea behind LQR, iterative LQR. You can apply this to lots of nonlinear systems. If you're interested, there's like a really cool paper that my PhD advisors wrote like 10 years ago called Guided Policy Search, which shows that you can use these for like robotic manipulation and like heavy contact tasks, which is a variant of LQR. So you guys should read it. It's a great paper. Okay, so our agenda today is super short. Basically, we're going to go from LQR to MPC, Model Predictive Control. And then we're going to talk about this idea called Lyapunov stability that I think is really awesome. Okay, so we've been talking about optimal control. And so the goal here is to want to minimize the sum of costs. We want to find the action UT or a control law that's going to minimize the sum of costs, right? And we've said that if F can be nonlinear or costs can be nonlinear, dynamics can be nonlinear, non-quadratic, right? And what we do is we often try to approximate these with things that are linear and quadratic. So we can try to approximate the cost with a quadratic approximation, which means it's a second order Taylor approximation, right? Or you can try to approximate the dynamics with a first order Taylor approximation, then becomes LQR, right? And that's reasonable. But like the world is not really linear and quadratic, right? And so the problem is that the approximation might be kind of poor. You might not be able to incorporate constraints that are hard to linearize. And so like, in general, it's not always a winning strategy to convert a nonlinear system into a linear system. So what we're going to try and do in the next few minutes is try to find a set of techniques that can actually work for a nonlinear system without converting it into LQR. Okay. So how are we going to do this? We're going to revisit some ideas we had in Bayesian filtering, right? So if you remember how Bayesian filtering went, we had this like Bayesian filtering problem that's hard in general. So then we said Kalman filtering is linear Gaussian, right? Then we said extended Kalman filtering is nonlinear Gaussian. Then particle filtering was nonlinear non-Gaussian. And so we're going to try and instantiate something that is almost particle filtering like. And so if you remember how this worked, when filtering, you had a Kalman filtering problem, which is linear and Gaussian. You had a sampling-based approximation to that, which was particle filtering, right? So it's kind of like trying to replace analytical solutions with samples. In control, you're going to have something similar. You're going to have LQR, which is the linear Gaussian solution. But we're going to cover something called sampling-based MPC, which is essentially the equivalent of particle filtering for control. Right? So basically, it doesn't need your system to be linear. It doesn't need your cost to be quadratic. But you're going to replace an exact closed form solution with an approximate sampling-based solution. Right? And so the idea behind sampling-based MPC is kind of the same idea that we used to go from Kalman filtering to particle filtering. We're going to use a similar idea to go from LQR to sampling-based MPC. Okay. As you'll see, basically we keep reinventing ideas and giving them good. And so that's the key to research. Okay, so the idea behind sampling-based MPC is to solve an optimal control problem with sampling, right? So we're saying that we want to solve this problem. We want to minimize the sum of costs. We want to find the set of controls that do so, right? Here's a simple way to do it, which is just sample a bunch of controls, run the controls forward through your forward dynamics model, right? Get a series of states. So let's say you start at some state X, run some set of controls forward, run a different set of controls forward, run like k different controls forward. For each of them, you're going to get what the state is going to be by running it forward through the F. And then let's say each of them has some like cumulative cost. You pick the trajectory that has the best cumulative cost, the lowest cumulative cost, and execute it, right? And so this is like a technique called random shooting, right? So it's like you're shooting darts. It's called random shooting because you're like shooting actions forward, right? But basically what random shooting is doing is it's like saying you're gonna start from some state x0. You're gonna sample a bunch of random actions. You're gonna roll those random actions forward through your model F. You don't need the model to be linear or anything. You just need to be able to go forward through your model. And you're going to evaluate all the states that you got to while running those actions by like measuring what their costs were, right? And so then you get, that is the cumulative outcome of executing those actions. You run this many times. You pick the best outcome that you get, and you execute those actions, right? So you run this many times. You choose the minimum cost trajectory, and then you execute the actions with the minimum cost trajectory. So like a valid way to do it. What's the challenge with just doing this?
It's projecting very far into the future, especially in the language that is dead reckoning. Is who knows if
Right.
that turning the
Right. We have dead reckoning problems, which means like drift or like whatever, drift from your true thing because your model is wrong, right? One thing is that, hey, your model is a bit wrong. That could lead to a problem. What are other problems with this approach? Yeah. Right. We have computation. Yeah, so it's hard to run in real time. Nice thing is like GPU parallelization can help here, so they're like parallel, but still, here is a big problem. The other thing is like, imagine that you had a humanoid, that you're trying to control a humanoid. What you're saying is I'm going to sample a bunch of random actions and then hope that the humanoid like accidentally backflips in one of them. And I don't know if that's going to happen, right? So there's like a challenge of like something called a curse of dimensionality, right? As your system gets larger and larger, it becomes harder to randomly chance upon good outcomes. And curse of dimensionality is inherently connected to exploration, right? So you have to explore the world to find good outcomes. Unclear that it's easy to do. And so all of these kind of make this random shooting strategy hard to use, right? So we're going to try and fix these problems one by one. But in general, no one uses random shooting as it. So random shooting says, let's choose the lowest cost sequence of actions and execute them openly, right? Which means that I'm going to just execute those controls one after the other. You can do this softly. You don't have to take the argmin. You can take the soft min, and that's basically just like the argmin. It would say choose this guy. The soft min it says like get a distribution proportional to negative cost. So it says like sample actions proportional to their negative cost. And so that means that I wouldn't always take the lowest cost action. Sometimes I would like put some likelihood on the other actions. That tends to like give it a little more entropy. But this is generally not a great strategy. So it's not a great strategy because of some of the issues that we talked about. We talk about the first issue, right, which is that your model is wrong. Your real world doesn't quite behave the way your model said it would. And so if your model is wrong, it doesn't quite behave the same way, then you start to like deviate from what you thought you were going to do. And if you're doing essentially open loop execution, it's like dead reckoning. It's like hard to come back here, right? And so you have this kind of drift. So if I wanted to solve drift, how would I do it? Like like the problem right now is we got a set of actions we thought were optimal and we executed them and the model is a bit wrong. And so we like kind of went off what we thought we were going to get.
Yes, one solution is we could use the
That's right. So that's all that model predictive control is. It's just a fancy word for saying recompute, right? And so we were just talking about, okay, your model is wrong. You see unexpected things. You're saying that compute is expensive. And so what's going to happen is that you'll start to deviate. Instead of just doing open loop execution, we're going to do closed loop execution, which means we're going to like recompute plans every so often. And so lots of issues with this model, but we're going to try and address them with the simple idea of recomputation. And so the idea of model predictive control is that you're trying to avoid the issues of open loop control, which, not able to be dynamic, heavy compute, kind of like model errors by just replanning, right? And so you're saying that like, what I'm going to do is instead of doing open loop execution, I'm going to, replan every so often. And so the idea behind model predictive control is just that you solve your planning problem, you execute one or a few steps of your planning problem, and then you replan again, right? And so it looks something like this. You choose your best controller, you execute the first step or the first few steps. It didn't quite do what you thought it was going to do. So now you're in a new state, right? And then you just replan. And so what replanning here would be is that you again do random shooting. You just shoot a bunch of random trajectories, you pick the best one, you execute it, and then you repeat. Right? Seems pretty simple, but like what it ends up doing is because you're like replanning, it places less burden of optimality on your current planner or your controller and it's kind of like allows for lazy computation. It says that I like can be kind of suboptimal now because I can fix it in the future. Not always, but in many cases. And so the idea behind model predictive control is that you're gonna solve a controller approximately, execute the first step or the first few steps, and then replay.
Do you get like a higher chance of having a better random case, or is it always? Or
I think it's hard to say like a catch-all statement across systems. Like some systems are more like funnels near the end. Some systems are kind of equally hard at the start. Like for instance, let's say you're doing pendulum swing up or something, right? Like it's kind of easy at the bottom, but it's really hard towards the end. Versus if you're like just trying to reach a goal in the plane, kind of equally hard. So a little hard to say generally. But the nice thing about model predictive control is it kind of gives you the flexibility to choose how much you want to plan at different points. So you can say, I kind of don't care at the start. Like in some ways, what's nice about the start is that you have more opportunities to fix yourself in many problems, not at all, but whereas at the end you don't. And so you can say, I want to do less computation at the start and I can do more computation at the end. I want to get. Okay. So the idea of an model prediction control is just saying that I'm going to do this replanning, and doing replanning is going to allow me to deal with these kinds. It's going to allow me to deal with these kinds of like issues that I had earlier, right? It's going to allow me to deal with each of these issues. If I'm going to do replanning, I can deal with unexpected events that come up. If I'm going to do replanning, I can do cheaper computation at each step because something in the future will take care of it. If I'm going to do replanning, I can account for model errors because it's like you're always checking your work, right? You're never like just letting things fly. So it's kind of like feedback. It's like kind of like what we did with Bayesian filtering. It's like you're not doing just dead reckoning. You're like updating your things with more information. And so the idea in model predictive control is just replanning. We are going to avoid this kind of situation where you go fully open loop. And so you're going to start by planning with random shooting from your first state. Right. So this is all in imagination. Right. So you can kind of think of this as like all happening in imagination. You start by planning with random shooting, which means that you're going to like, at this state, you're going to like execute a bunch of stuff, choose the best one. Let's say this was the best one. You're going to like execute the first guy. You're going to get to a new state. So you're going to execute it not in hallucination, you're going to execute in the real world. And then you're going to like go back into hallucination and plan again. Right? You can, if you want, you can call this deep seek. It's kind of the same thing, kind of like reasoning. So deep seek is really model-based reinforcement learning, or I guess not deep seek, but like reasoning models. So yeah, the point here is that you're going to like do random shooting, choose the best thing, execute it, and do planning again, do the best thing, execute it, repeat. Right? Alrighty. So it kind of looks something like this. You're going to do some planning. You're going to then do some doing. Then you're going to do some planning again. And in practice, you often don't do this at every time step. You like do some planning, execute some number of steps, do some planning, execute some number of steps. But it like allows you to like kind of operate like this. So let's say this was your plan. You didn't exactly do what you expected. So you're going to do a replan. And just, so like, for instance, if an obstacle shows up, you're able to like avoid it in real time. And so that's the simple idea behind model-based, model predictive control. Okay, so here's some examples from some folks over at Berkeley. They had this like little hard to see, but they had this little cockroach. And so they made this cockroach out of like plastic and 3D printed material. And it's super, super hard to model. Right? It's really hard to build a model. So what they do is actually learn a neural network model, which is going to be wrong. But then they do model predictive control to like have it navigate around. And so what's really awesome about this is that your neural network model is not very good in the long term, but it's really good in the short term. And so model predictive control allows you to take lots of short-term things and kind of put them together. And this one is like a weird Mujoko snake, but I think it's called the swimmer, but you can see, do I have a codec problem? Okay, but you can see like different creatures can go around with basically model predictive control. Now, the nice thing is if you're ever trying to solve a problem in simulation, you have the model. Like there's not always a good reason to run reinforcement learning. Often model predictive control is really effective. Right, so you can kind of, we'll talk about reinforcement learning in a few weeks, but like often in simulation, model prediction control is great. In the real world, it's hard because you don't always have a good model. Right? But in general, the idea is you would start like you're avoiding linearity, you're avoiding quadraticness by just like relying on sampling. It's like you're just shooting darts, seeing which one sticks the best, executing, and then shooting darts again. Yeah, that's it. Like random search. And it works surprisingly well. Okay, so we solved some of the problems, right? So we talked about dead reckoning problems. We kind of like did a little bit better there. We talked about compute problems. We did kind of better there. What are remaining problems?
Yes, there's a problem with actually choosing your random actions.
Actually choosing your random actions, right? So the tricky part is as you go to high dimensional long horizon systems, it's unlikely that just random actions will get you anywhere, right? And so basically you have this needle in a haystack problem. You're just trying to shoot. You can kind of think of random shooting as like you're like shooting a string out and you're hoping that it like gets to like the treasure that you're looking for, which is like low cost. But it's in a high dimensional system, this becomes exponentially less likely. Right? And so the problem is that we often call this problem variance, where you need like a huge number of samples to actually get any signal. Right. So to the point from earlier, we have this like compute problem, which gets even worse in a high dimensional system because you have to take so many samples to get this thing to do it. Okay, so we have this variance problem. How could we fix it? Yeah. So high dimensional system, just shooting random actions, unlikely to randomly hit the code. Yeah. Okay, so we could set a target. I guess the tricky part is you don't know how to manipulate the dynamics to get you to the target, right? So it's like, let's say the target was like humanoid backflips. It's like what you need to do is you need to choose the sequence of like controls on the joints to get you there. So it's like even then it's like hard to know what those would be. Right? Yeah, exactly. Like, but you can't do dynamic programming because it's not LQR. So LQR is going backwards because it is LQ, and now we're not LQ, and we're going forward. So how do we? Let's think of like what are ways we can make this a bit better.
Yes, like if you know the cost function, instead of just trying like everything, maybe like let's say you know that you have to get to the point, like lowest cost would get it.
Right.
So
So yeah, so that's like an interesting idea, which is basically like the problem with the straight line is that it's not dynamically feasible,
Yeah.
right? And so one thing you could do is you could start from a non-dynamically feasible trajectory and then like sample around it to project it onto the dynamically feasible set. But that can sometimes be hard. Like with a humanoid, it's not even clear what the like trajectory would look like. But the intuition you just said is basically what we're going to build on. It's basically that you don't need to sample. Right now, what's happening is you're sampling randomly. So you're sampling views randomly in the range of all possible actions at every step, which means like every step you take a Gaussian centered at 0, variance 1, you're going to sample an action. You're going to do the same thing again, the same thing again, the same thing again. Right? But really what you care about doing, you care about sampling things that are close to things that are low cost. Right? And so the idea here is that you don't want to sample from a uniform or Gaussian distribution every time. Instead, what you want to do is you want to be a little smarter about sampling by using the cost function, right? So it's like, it's kind of like a follow the nose type of intuition. So it's like if I sampled some random actions, I saw that I was getting closer to my target. I shouldn't be sampling here anymore. I should spend all my sampling effort near where I'm trying to go, right? For things that are local. And so the idea behind this method called MPPI, Model Predictive Path Integral, you read the papers, they're like wildly confusing. But all that it's saying is that you're going to iteratively upweight the sampling distribution on things that are low cost. That's it. Right. And so the point here is that you're going to like sample once, right? So this is all in imagination, right? So you're going to sample once, you're going to get something that is low cost. So you're going to get like cost 1, cost 2, cost 3, cost 4. And you found that like this thing was low cost. What you're going to do the next time is you're going to like sample. We do have an animation here. You're going to sample more near the thing that is already low cost, right? So you're not going to waste time sampling here. You're just going to sample in the neighborhood of things that are low cost, right? And so the point here, the way you're going to do that. Okay, so the way you're going to do that is that you're going to start by like sampling a sequence of controls from some distribution P, right? So initially you'll start your distribution P at some uniform distribution or a Gaussian, you're just going to sample actions. You'll get a bunch of trajectories, right? You'll roll them forward through your system, you'll get a bunch of trajectories. You'll then weight each trajectory by the exponential of the negative cost, right? And it needs to be exponential because you want it to like be positive. And so you're going to say you're going to weight it by the exponential of it doesn't have to be exponential, it just needs to be any like monotonic positive function. But like exponential of the negative cost. So things that are low cost will be weighted high, things that are high cost will be weighted low. And so you're going to then say like your sampling distribution PU gets updated to something which weights low cost things high and high cost things low. And so now your sampling distribution is far closer to the things that you care about, and now you're more likely to do better here. And then you repeat, right? So the idea behind MPPI is just you do this iterative reweighting of your distribution by like reweighting it by the exponential of the negative cost, right? So earlier what we were doing is, let's see, do I have this on the next slide? No. Earlier what we were doing is, let me go back a few slides. We were kind of doing this process, right? We're sampling a set of actions, evaluating each one, choosing the minimum cost, executing the lowest cost action, and repeating, right? Now what's going to happen is inside each loop of imagination, you're going to repeat this thing k times with an updated sampling distribution. Yes. One way of thinking of the like resampling thing for FUPI is that it's kind of like you can kind of think of particle filtering from this perspective of something called importance sampling. And so you can think of like the reweighting step of a particle filter as doing importance sampling, where you like weight the particles. And in some ways, what MPPI is doing is it's changing the like sampling distribution through something called importance sampling. And so the connection between them is through this importance sampling. But a little out of scope, so we'll talk about it. But it's cool. You should look up importance sampling and read the MPPI paper. Like that's the easiest way to connect. Good question. Okay, so the idea behind MPPI is simple. You sample a bunch of stuff, you roll them out, you reweight them by the exponential negative cost, you update your sampling distribution, and you go get. And so what it moves your sampling distribution closer to things that are low cost. And if you just do this, right, you can actually show that this is like the lowest variance distribution that you can have to sample. But you can actually apply it to lots of real systems. So here's one that Byron Boots did. My videos are not playing, but it's like this high-speed drifting, car drifting on a dirt track. And so obviously your model for the dirt track is not going to be perfect. Like how do you model all of the dirt? But he's basically doing model predictive control with MPPI. And so you can see that well, it's a little hard to see because I'm like speeding up the video, but it actually goes pretty fast. So it's able to operate at close to real time with not that much onboard compute. And like here they do a learned model, but you could also have a hand specified model. And then you can take this to the like more extreme version, which is this like DARPA racer program, which Byron Boots leads. But basically they applied the same MPPI style algorithm to like autonomous vehicles on off-road terrains. Sorry, I'm just gonna restart this and see if it plays. No, it doesn't play. Okay. But basically you can see that it like goes through all sorts of different terrain, all of which is pretty hard to model. But the trick is just don't try to model everything perfectly, just replan enough that you can recover, right? And so you can see it kind of is quite robust to different types of terrain, different types of perception, and so on, all with the same MPPI algorithm. So it kind of really works in the real world. Now, what are some, I'm not saying it's magic sauce, right? What are some challenges with this kind of method? Like, when might it not be good? Or what might make it like hard to use? Oops. So we're just doing the iterative regrading thing. Like, when is that not very good? Exactly. So there's like a inherent exploration exploitation trade-off, right? So it's like this is kind of the whole problem behind reinforcement learning too, and MPPI too, is basically you're being kind of greedy. You're saying that I'm gonna like just pick the stuff that is like low cost. It's not like just argmin. You're like it's soft, like soften, but you still like are kind of going towards things that are low cost. And so like let's say you like accidentally sample something that was like low cost, but you had a different thing that was lower cost, you like start to miss that. And so there's an inherent trade-off between when you exploit versus when you explore. And so if you're interested in that stuff, look up like upper confidence bounds and exploration in reinforcement learning. It kind of tries to tackle that. What's the other challenge that comes with this kind of method? Another challenge is compute, right? Like you're repeating this process like k times. Now, earlier we were already doing expensive compute by running the model forward. Now you're saying I'm going to do it like k times in the loop every time I make a decision. And so if you want to be real time, it can be harder for like larger systems. Okay, so that's the key idea behind model predictive control. How do we feel about it? Questions?
It's not like really high dimension. What do you get a good first estimate that isn't this?
That's a great question.
thousands?
That is a hugely important question. What a lot of people do is they like relax the problem. And so they like, for instance, will relax constraints, they allow you to fly through free space or something like that. And then you like sample around a relaxed solution. The relaxed solution is easier to compute, but it's not correct. But it might give you a good guess. The other thing that people do is they like use learning to initialize a good guess. So they like solve a bunch of expensive problems with tons and tons of compute. And then they like have a learning-based controller that proposes the best first guess, and then you refine that. Those kinds of things. Good question. All righty. Should we go to Lyapunov? Okay. So the Lyapunov is, I think it's an awesome idea. But basically it's kind of like we've been talking about synthesizing controllers, which is like how do we design a controller that minimizes cost? What Lyapunov's stability tries to talk about is how do we guarantee that those controllers are stable? And so when you say something is stable, at this point we're going to say something where the error goes to zero at asymptotically, and the gradient of the error goes to zero, which means that your system is at rest. Or it doesn't have to be at rest, but it has to be like at a 0 point. Now, the zero doesn't literally have to be zero. You can shift the reference with a change of variable, but you want your system to like converge and be stable, right? So if it's like a pendulum, you want it to swing up and stay there. If it's a car, you want it to get back on track and stay there, right? And so the point of many control systems is to ensure stability, right? And what Lyapunov theory tries to do is it tries to provide a way to verify if the controller is stable or not. Right? And it tries to do that in like a cheap, practical way. So let's consider the system, a pendulum, right? So the pendulum, it's got a mass m, your moment arm L, gravity is going down G. Your angle from the vertical is theta, right? And so just by like equations of motion, you can show ml squared theta double dot plus mgl sine theta is equal to u, kind of what we did earlier too, yeah? And so if you have this kind of system, what happens if u is equal to 0? Is the system stable? And let's say it didn't start at rest. Let's say it started like out here. Like someone started out here. Like, is that system stable? As in, will it go to the 0 point and stay at the 0 point in the limit? Right, so what we want is like, we want to synthesize a control law. U is equal to some control law, phi or k or whatever. That like, that sends theta to 0 and sends theta dot to 0 at convergence, all right, in the limit of time. So the question we want to ask is first, if I set like u equal to 0, the system is not stable. So what's going to happen? Imagine you had a frictionless pendulum and you just like allow it to keep swinging. It's just going to keep swinging. There's no reason for it to stop, right? It's going to oscillate between kinetic energy and potential energy. It'll swing, and it'll swing, and it'll swing, and it'll swing. But there's no reason for it to be stable. And so a passive dynamics pendulum for a frictionless pendulum is not stable, right? Which means that it's never going to converge to theta equal to 0 and theta dot equal to 0, right? So we want to put in some controls into the system. We want to choose a u such that the system is going to become stable, right? Which means that I want the pendulum to really come to rest at 0 with theta dot, which velocity is 0, position is 0, asymptotically, right? And so what we're going to try and do is we're going to try, we saw that u equal to 0 doesn't give you that. So it's not like passively stable. We're going to try and verify if a particular controller is stable, right? So does the controller force the system to go to 0? And so we're going to try and choose a particular one. Let's say u is equal to minus k theta dot, right? And so you often call this damping, right? But u is equal to minus k theta dot basically says you apply a force which is opposing the velocity, right? And so the thing like velocity is going this way, I'm going to oppose force this way, right? And so intuitively, you kind of feel like it should get the pendulum to rest, right? When it's going this way, you're opposing force this way. When it's going this way, you're opposing force this way. So it's trying to bring you back to rest, right? But how do we know? if I'm flying an aircraft or I'm flying like a helicopter, I really need to know that it's going to be stable. I can't just like go on vibes, right? And so how do I guarantee that the system is stable? And so one thing you could do is you could just like try the system from a bunch of different positions and like check, is it stable? Is it stable? Is it stable? Is it stable? But it's hard to like guarantee that you can cover the space in any large enough system, right? Because there's like an infinitely large number of initial conditions that you might have, right? And so you might miss some points and it's not immediately obvious that the system is stable. And so the idea behind Lyapunov theory is to go back to like ideas like energy, right? So it's saying that like, can I show that with this controller, the energy of a system will go to 0? And if the energy of a system is 0, that means theta is 0 and theta dot is 0. And so it's gonna introduce V here. It's often called a Lyapunov function, but it's basically it's the analog of energy, right? It's gonna try and argue that the system has an energy which is decreasing, and it's like energy is always positive. It's decreasing, and it's going to get sandwiched so that it eventually goes to 0. And so the key idea of Lyapunov theory is like, let's try to design something that looks like an energy. And like, let's show that energy is decreasing, but always positive. And if something is decreasing, but always positive, it has to go to zero. Right? Or always non-negative. So the idea here is let's like literally look at the energy, right? So the energy here is the sum of the kinetic energy and the potential energy. It's a half ml squared theta dot squared is the kinetic energy. And mgl 1 minus cosine theta is the potential energy. We know this is always positive, right? So you can check that because this thing is positive. This thing is always positive, right? So this is a positive plus a positive, always positive. So the energy V is always positive. And what you want to then check is V dot, right? So whenever you do dot, that means the derivative with respect to time. Okay, so V dot is basically dV dt. Okay, and so you're going to take the derivative of this thing with respect to t, and you can kind of like write it as dV d theta times d theta dt, right? Just by chain rule. And so if you take the derivative of this thing, the first term will give you ml squared theta dot times theta double dot. And the second term will give you mgl sine theta. You can just like take the derivative of this thing. I'm going to skip the calculus here for time. So this is V dot, right? This is the gradient of, this is how the energy changes over time. Right? So it's like, which direction is my energy going with time? Now you can sub in from the previous slide, you know what theta double dot is from your equation. You know that theta double dot is this guy, u minus mgl sine theta, right? You just substitute that back in and you just do a little bit of algebra. You'll show that the gradient of the energy is theta dot u. Okay. And now if you set u equal to minus k theta, if you set u equal to minus k theta dot, you can show that v dot, which is the gradient of energy, is minus k theta dot squared. K theta, this theta dot squared is always positive, k is positive, which means that minus k theta dot squared is always negative. Okay? Which means that like your system is always reducing its energy. Like you can kind of think of that V dot as like which way is the energy going? That you're saying that with time, your system, if you fed the control law in as minus k theta or k theta dot, you can show that the energy is always reducing, and you know that energy is always non-negative, which means that this has to, it's like a sandwich, right? It's like you have a thing that is going down to zero, and the system is only equal, the energy is only equal to zero when theta is equal to zero and theta dot is equal to zero, which means that the system has to converge to something where theta and theta dot are zero. Eventually, it's not saying how fast it converges, it says that it will converge, right? And so that's the key idea behind Lyapunov theory. It's just saying like, find a quantity that is non-negative, and it's only zero when theta and theta dot are zero. Then show that that quantity reduces over time, right? And in this case, we chose energy. Lyapunov says you can choose any other function. We'll talk about that in a sec. But it's just saying it's just a sandwich theorem. It's just saying like you have something that's always positive. It is decreasing over time. It's only zero when the system is at rest. It has to go to rest, right? Or it has to go to like a stable point. And yeah, that's basically it. But I think the beautiful part about it is that you don't have to actually know the control. You don't actually have to like check the controller everywhere. You just need to design a function v, which allows you just have to prove two things. You need to prove that it's non-negative and only zero at zero. And you have to prove that it's decreasing over time. That's it. Right. And so all that a Lyapunov function is a generalization of energy. Right? It's like, it doesn't need to be literally the energy of the system. It is like a function that is always positive, unless you're at the final point, which is, in which case it's zero. And it is always reducing with time, which means that the gradient of that function is negative. So the conditions for a Lyapunov function are that v of x is greater than zero for all x, but it's only zero at the origin. So you want v of zero to be zero, and v of x is greater than zero for all x that is not zero. Okay. And you want v dot x is less than zero for all x, right? Except for the origin again. So you want v of zero equal to zero, you want v dot of zero equal to zero, but you want v of x to always be non-negative, and you want v dot of x to always be negative. Right? So it's like you're sandwiching this. Yeah. Yes. Like, I guess it's like, it has to, like, if you had a local minimum, these conditions wouldn't be satisfied. Right, so like, imagine you had a local minimum, right? So imagine you had something like that, right? Like the non-negative would be satisfied, but this gradient became positive here, right? And so you're saying that like, if you have a local minimum, then this is not always reducing. Right. So like if you like you need it to always be reducing, you could have something that like, for instance, looks like this, and that's always reducing. But as soon as you have something that like increases, right, then it's like no longer satisfying this criteria. Yeah, so the way that the control law is linked is that V dot is basically dV dt, right? Which is basically dV dx times dx dt. And dx dt is linked to the control law through the dynamics of your system, right? So if you're like, let's say your system is continuous time, you can show that dx dt is basically the dynamics of your system. You'll have like x dot is equal to f xu. And so like your control directly determines v dot, right? And so there's like different variants of Lyapunov. You could have Lyapunov for a passive system. You could have Lyapunov for an active system. For an active system, the control determines if your system is Lyapunov or not, or you're trying to verify whether that controller is going to be stable. And you can also have like these ideas called control barrier functions and control Lyapunov functions, where you're trying to like get a system to be in a safe state. So you're trying to like have a controller and you're trying to say, well, this is not going to be safe. Let's do this thing. This will be safe. I guess I have a minute left, but the idea is basically have something that's non-negative, but only 0 at 0, and show that it's decreasing. So to Marcus' point, it's like it cannot be increasing. So I guess in some sense it cannot admit local optima, and then it'll converge to 0, right? So you can show this for the car. I don't know if I'll have time to do it now, probably not. But basically you can run through some algebra for the car, where you can choose a function that looks something like this. E cross track is like the cross track error. Theta E is like your steering angle. And if you choose a Lyapunov function like this, you can show that V dot for a particular control law will be negative. You can show that V will always be positive. And so you'll get a stable controller for your car. Right? So the nice thing about like a Lyapunov controller is that it's easier than synthesizing the control law. You're not trying to say that you're not trying to solve an optimal control problem. You're just trying to show these like kind of loose conditions. We're just trying to say something is positive and something is decreasing. That's it.
You model your dynamics would be, and then fix it.
It's more like someone gives you a control law, and then you're like, I need to verify that it's stable. And so you try to design a Lyapunov function where V is always positive and V dot, when you're using that control, is always negative. And then you can verify that your system is stable. And so often it's a bit of an art in how to choose the V. I don't know if there's like a one size fits all here. But if you can find a V, then you have guarantees that your system will be stable. If you can't, then yeah, exactly. Then you have a problem. Okay, cool. All right, that's Lyapunov. I will see you all on Wednesday. I'll be on Zoom on Wednesday, but I'll be around. All right, thanks, folks.